All right, and welcome back to our reading of categories and sheaves. We're picking up where we left off. I'm going to remind you where we left off in just a second, but we're reading chapter 3 of the book on filtrant categories and filtrant limits. And the last proposition that we had discussed was a proposition which enabled us to describe these limits in a relatively clear way. We do this basically analogously to the construction of the p-adic numbers. So let's just remind ourselves of this proposition. We have alpha, a functor, with I, a small, and filtrant. Oh yeah, it reminds me. Some people call these filtered, but we're going to follow Kashiwara and Shapiro and call them filtrant. So what we do is we define an equivalence relation on the coproduct of all the alpha i's. So we form this big set, and we declare x equivalent to y if and only if there's an x in alpha I and a y in alpha j, with, of course, these guys should be different, and a pair of morphisms s I to k and t j to k, such that alpha s applied to x is alpha t applied to y. So what is this saying? Well, it says that if I take a pair of guys, two generic elements in this big coproduct, then what should happen here is I have I and j both mapping into k, and this is part of some big tree, so to speak, or big graph, if you like, of roofs and, well, I don't know what to call them. They're like equalizers, but they're not universal. I'm just going to call them parallel morphisms. And among these array that we have of objects, whenever these objects commute, we call these things, we declare these things to be equivalent. And under these conditions, what we saw was that, of course, this is an equivalence relation, but in particular, I won't write that part down. What I'll write down is then the limit of alpha is this coproduct modulo this equivalence relation. And so this is a sort of tool for computing with, right? In the sense that for any practical purpose, if you know all the objects, then you can say what all the elements of the coproduct are, and you know this equivalence relation, so you can say when two things are equivalent. So you sort of have a recipe then for describing elements of this coproduct. Now there's a corollary of this, which Kashiwara and Shapiro leave as an exercise, but I hate this because this was their motivating example. So I want to fill you guys in with a proof. So let's write down what this corollary is. The functor f, the forgetful functor, I'm just going to call f, from modules over a commutative ring, I get, you probably need a 1, but I'm not going to worry about that, to sets, commutes with small filtrant limits. And they just basically completely leave this out. I think they think it's obvious, but it's not super hard, but it is a little bit of a calculation. And so I'm going to show you how to do this calculation because when I was reading this, I didn't find it easy to see. In fact, I think I had to fish it up off of the internet because I myself am a bit of a novice to category theory. So let's see if we can make this clear. So the previous proposition gives us a description of this limit. What we want to do is show that under these hypotheses, we can use the forgetful functor and we can transport a group operation. That was the big problem. You might remember from the motivating example that we gave back in the beginning, is that in general, the failure of these things to commute is basically the failure to define a group operation in general. So what we want to do is make sense of that. We want to show that such a thing can always be defined. Now, the multiplication map is not that hard to say what it is. Once you have an addition map on the disjoint union, then you just take everything factor-wise. Since they're all modules over some ring, there shouldn't be any problems. So it seems reasonable for us to focus on just the group structure. In other words, just the additive part of this. So I'm going to write that sort of, I'm just going to write multiplication seems clear. And if you're not happy with it for some reason, then feel free to leave a comment and we try to figure this out. What we're going to do is focus on the additive structure. And so for this reason, it suffices to work with Z modules. In other words, abelian groups. So now let's fix some notation. We're going to call the maps into the limit by lambda I. So we have these maps lambda I, alpha I to the limit. And from the proposition, we know how to represent these as equivalence classes. So in particular, we can write them as pairs. I, x, as so, for some x. And the equivalence relation lets us say that Ix is equal to k alpha f of x. Let's just make sure I get these parentheses placed okay, like so. Whenever f is a map I to k. And so with a pair of such classes, we're going to define the addition as follows. We write Ix plus jy. This will be k alpha f of x plus alpha g of y. And so the idea is that we have this sort of roof that lives over each thing, and when we take our I and j and we pass to the common k, and then we use the operation wherever we land suitably. And we need to check that this is well defined. This is, of course, the bit that actually requires the work. So for here, we're going to use our previous results. So suppose we had another pair of representatives for this guy. Let's call them f prime and g prime. Then what we want to do is use what we saw above, namely that there's an h, which is k to t, and an h prime, which will go k prime to t, such that hf equals h prime f prime. And hg is h prime g prime. And now from this, what we see is that we can calculate. We can write alpha of h, alpha of f, x equals alpha of hf applied to x, which is alpha of h prime f prime applied to x, which is alpha of h prime alpha of f prime of x. And we can do the exact same calculation with g and g prime and y. So what this does is it swaps the equation, changing f into f prime. And so in particular, this equation does not depend on the choice of representatives, and therefore we have the desired operation. Okay, now maybe I should write a sentence. Same for g, y. So nothing depends on choice of representatives. And I put the little box because I think that's pretty much it. Okay, I want to do one more theorem in this video. I'm basically trying to wrap up the stuff from the first part of 3.1 that we didn't get to last time. And so I want to include now a theorem that relates commuting limits and colimits, the other sort of natural application for all this. So here's a theorem. Suppose that I is small, then the following are equivalent. First, I is filtrant. And 2, for any finite j, and functor I cross j op to set, then the natural morphism, and let me make sure I get this right. First we have the limit going in over I, and then the limit going out over j of alpha ij to now the limit out over j, limit in over I, alpha ij, is an isomorphism. In other words, lim, forward lim, commutes with finite projective limits. Okay. So one direction is slightly less painful than the other. We're going to do the more annoying direction first, sort of tear the band-aid off, as they say. So first, we'll assume that I is filtrant. So now, since every projective limit is a combination of kernels and products, we saw this back in like chapter 2, it's enough to show that lim commutes with these guys. With kernels and actually, this is a finite setup, so finite products even. But that's sort of neither here nor there. Okay, so for kernels first, this is why this direction is more painful, because there's somehow like bullet points to this proof and then like sub-bullet points and so on. So for kernels, let's let alpha and beta, I to set, be two functors, and fg alpha to beta, two morphisms of functors, I guess natural transformations. And sometimes I'm going to do this thing, I do this in my notes, they're teched, but I'm not that good at LaTeX either. F and G are supposed to be a pair of parallel morphisms. So I only wrote the one arrow. I just wrote in the second one to try to squeeze it in. Invariably in these arguments, I'm going to mess this up. So please just sanity check what I say and what I write. Sometimes a single arrow is really meant to denote a pair of parallel arrows. I'm going to try to make that always clear from the context. Hopefully it doesn't cause any headaches. So we have our pair of parallel morphisms. Now let's take gamma and let gamma be the kernel of this pair. And recall what that means from 2.4 or whatever, 2.3. Gamma, the kernel of this pair. Then we have exact sequences. That's what this means. We can go gamma I to alpha I to beta I. Now, we can consider the kernel of the limit. So denote by Z the kernel of lim alpha I to lim beta I. We need to prove that our lambda, well, actually, this is different from the lambda before. I still use lambda in my notes, but it's not the same lambda as before. Need to prove that lambda from limit gamma I to Z is a bijection. So the idea of our proof is that our definition is that a kernel is this equalizer. And since we're doing this on the level of functors, we think of this as a family of equalizers indexed by the category I. So our plan is to just bundle these together. And then, since both of these objects are essentially initial objects over the equalizer diagram, they should be the same. Because they're both initial objects over the equalizer diagram. Okay, so now we have to sort of make a sub-bullet rather, where we have to prove this is a bijection. So first we do surjective. So for surjective, take some, that's supposed to be an x, take some x in z, and we represent this by what's basically a sequence, xi and alpha I. Then we have fi xi and gi xi have the same image in lim beta, or I should say, if they have the same image. That's the same thing as saying that we have an S, or an SI rather, I should probably make these indexed to J, such that beta of these guys makes them map onto each other, as we saw above. So what we do, I think actually I don't need to index these. I think I just need an S. I was a little worried about that a second ago, but now, oh, I didn't even write the indices there. I think it's just some S. Of course, it should go I to J. But I don't think I need to index them because I think I only need the one S. Anyway, so I have S, I to J, and if they have the same image, then I can make this equation satisfied. So now I'll set xj. This will be alpha S xi, and from this definition, we see that fj xj is the same thing as gj xj as well. And this means that xj is, of course, in gamma j. Now, on the other hand, it's clear that lambda xj is nothing but x. And so this finishes our proof of surjectivity. All right, now let's do injective. So for injective, I take two guys xy in the limit of gamma with lambda x equal lambda y. And I represent x and y by elements. Again, I pass to this sequence representation. So I write these guys as xi, yi in gamma I, as I is an I. And now since these have the same image in the limit, I should write this down, these have same image in the limit over alpha. And so there's a map I to j such that they have the same image in some specific alpha j. Okay, and this is one of the previous corollaries that we saw. But this means that their images in gamma j coincide as well. So they're actually the same. And that finishes the proof for injectivity. Now the proof for products, maybe for the sake of time here, because we're already almost 20 minutes into this, maybe I leave this alone. I think Kashiwara and Shapira might also leave this alone. But the proof should be the same, morally speaking. The only difference is now instead of working with the equalizer diagram in the above part, you have to work with the product diagram. But the argument should be exactly the same. Okay, now let's do the reverse direction. And this one's not so bad. So here we use that lemma 3.1.2. So we consider a finite category J and a functor phi j to I. Now we have a characterization of filtrant that says that there is an I with the limit over the j's of Hom in I phi ji not empty. And so by the assumption, we have a bijection. Lim over I, other lim over j, I, alpha j, I. This thing is the same as in the reverse direction. Okay, but the catch is that on the right side, if I look at this here, that guy's a singleton. And this then makes the entire right-hand side a point, because I'm taking a limit over a bunch of points, so there's nothing to do here. And from that, that means that the left side must be, in particular, non-empty. And so this implies that the inside can't be empty, because I took the limit. I took a bunch of limits over things of this diagrams of this. I don't want to say shape, or with these objects in them. And so since I didn't get something empty, those limits must also not be empty, and therefore we've established that this category is filtrant. And that finishes the proof. Okay, so as a consequence of this, and maybe this is the big upshot for the whole section, we can combine this with the previous corollary. And what we see is that lim as a functor from the category of functors from I to R modules commutes with finite projective limits. Which feels like a pretty non-trivial fact in the world of maybe homological algebra, if you like. Certainly something that one sees quite a bit when one wants to do algebra. Maybe homological algebra is not, maybe commutative algebra. I don't know, whatever you like. Definitely feels like an important result. Okay, I think this is a good place to stop. I think I'll pick up next time with the IPC property. This should hopefully not be a tremendously long section. The point of just to maybe give a brief sentence or two about why this is important. The IPC property, sort of point of it is to give some conditions under which you can use these sorts of results, because these things don't necessarily hold in general. For example, in this hypothesis, in the previous result, we assumed that J is finite. But we don't want to work only with finite categories. We want to work with all sorts of categories. And so when J is small, there are lots of infinite small sets. Seems like a little bit of a funny thing to say, but I mean, there are plenty of these. And so the IPC property is a condition that you can insist on when J is small and discrete. So maybe in some ways less general, since discrete is sort of restrictive, but there's no size constraint for practical purposes, and that feels like a pretty big gain on the other hand. Okay, so I think I'll leave this here, and I'll pick up next time with the IPC property. And so until then, everyone, take care.